we are going to the last talk for today. This is Dr. Thomas Mejstrik, and the lecture is on the multiple subdivisions and the problem of the joint spectral radius.
With this, yeah. So wait, that's first. One moment. So yeah. Yeah. So thanks for the opportunity to give this talk here. I'm very happy. So this talk will be about multiple subdivision schemes, which are a generalization of subdivision schemes, and then I will also show how to prove convergence of those, and this will then lead to the joint spectral radius. So we start with an example of subdivision scheme. It's one of the first examples of subdivision schemes ever, the Chaikin's corner cutting scheme. We saw it also in the first talk of today. And so given a set of points, as we have already seen, we iteratively cut away all the corners of the points. So each point, here we have 4 points, is replaced by 2 points, and the new points are computed as averages of the neighboring points. So in the original scheme, we take 3/4 of the left point and 1/4 of the right point, and for the other point, vice versa. And doing this, we quite fast get some smooth limit curve. As Niradin usually says, 4 is infinity. So after 4 subdivision steps, one usually gets something nice looking. So how can we describe this algebraically? So I will do this in coordinates because then we can use functions, then it's easier to work with. So we have some data given. These are now sequences on the integers. And then we need a rule how to introduce new points. So how to refine our mesh on which the data lives. And then we need a rule how to compute the new points. This is in the corner cutting scheme. We take 3/4 of the left and 1/4 of the right point. And for the other set of points, vice versa, 1/4 of the left and 3/4 of the right point. And so we one subdivision step can be written as we have a sequence C and map it to another sequence where the even points are just the convolution with the one mask and the odd points are convolution with the other mask. And instead of, no, not instead, but now this new sequence are interpreted as data living on set half. But mathematically, we can identify this as the integers again. We can write this slightly shorter by using one formula instead of 2 cases, which looks like a convolution, but we add here the factor of 2. So we always choose the correct value of the set of the masks A0 and A1. And the 2 comes from the fact that we double the number of points in each step. So we will use this, we will see this formula later on. That's why I discussed it here. So what can we generate with subdivisions? Or I saw some examples here. At first, you can go to higher dimensions. So we can compute surfaces, as we have seen already today. Then something else, what we can generate are self-similar sets, fractals. That's not surprising because in subdivision we do the same thing all over again until we get something in the end, and so it's natural to expect some kind of self-similarity in the limit. And here we have the Sierpinski triangle and the twin dragon. So, but just examples. One application of self-similar things are refinable functions, which can be used for construction of wavelets. So this picture, we see the first Debussy wavelet or second or third, depending on the numbering. And this function is a shift. Also, the sum can be written as a, this function can be written as a sum of shifts and contractions of itself. So if we compress this function, shift it around and sum up all sums, we get the same function again. So what else can we do with subdivision schemes? Up to now, we use the same subdivision process in each step, but of course we can use different subdivision rules in each step. Also in the very first talk today, the way how we cut at the edges was not fixed. So if we do this for a scalar subdivision scheme with curves, for example, we can produce functions which are C-infinity and have finite support. That's not possible if we would do the same thing all over again. But in order to get something like that, we have to allow different data generations in each step. And then we can take this one step further by also allowing changes in each iteration, how we introduce these new points. So how to make a new mesh. And if we do that, we can construct something like you see here. This is a sequence of functions, an infinite sequence of functions. And the functions you see have the property that this function here, the very first, can be written as a sum of shifts and dilates of the second. So similar to the wavelet before, we have a kind of self-similarity now, but not with respect to the same function, but with respect to the next function in the sequence. So, and such a function, for example, can be used for a analysis of some data which has some directional features, because you see the functions we generated here rotate quite widely and also have very different shapes, but they still are self-similar with respect to each other. So they can be used for a multi-resolution analysis like we could do it for wavelets. And with that, we already arrived at the multiple schemes. And one thing we will see during the whole talk now is the joint spectral radius, so I just give the definition. The joint spectral radius is a generalization of the spectral radius of one matrix. So the spectral radius of a matrix is, we look at the growth rate of the matrix powers in norm. So matrix products of length n. And now the joint spectral radius takes a finite set of matrices and looks how does the norm of all matrix products of length n evolve with respect to n. So it's the worst case growth rate of matrix products from our set. So, and so we are at subdivision. So how do we define multiple subdivision? It's easier to have a look at the simple case of scalar subdivision first, and then generalize it to multiple subdivision. So we have a mask, the A. This was the rule how we compute the coordinates of the new sequence, and M is a dilation matrix now, which defines how we generate a new mesh. And the one condition we need to impose on this dilation matrix is that it's expanding. So otherwise, we would generate a degenerated mesh in the limit. So, and expanding means all eigenvalues are greater than 1, or vice versa, the spectral radius of the inverse is less than 1. And the subdivision operator then is defined as this kind of convolution we've seen before. And this, I say, a sequence of this subdivision operator is called the subdivision scheme. That's a really bad terminology, but at least it generalizes well. So And we say that S is convergent if there exists a function phi, continuous compact support, such that our subdivision scheme converges to this function phi. So remember, those sequences generated here all live on the S-dimensional integers, but we interpret them as living on integers divided by n to the nth power. And then, as with the wavelet, one can show is if a subdivision scheme is convergent, then this function phi, our limit function, our very basic limit function, has fulfills this self-similarity equation. I forgot to say what delta is. Delta is the delta sequence, which is 1 at 0 and 0 everywhere else. And so now we have a look on the definition of multiple subdivisions. For that, we have a finite set of subdivision operators, all defined with some data generation rule A masks, also masks A and dilation matrices M. Now the dilation matrices must be jointly expanding. So regardless in which order we apply them, the mesh we generate must behave nicely. And this can be expressed that the joint spectral radius of the inverse now is less than 1. The subdivision operator is defined as before, and we say any sequence of subdivision operators is a subdivision scheme. And convergence now is defined if we take any index sequence, then there exists a function phi to which our subdivision scheme converges. What about this self-similarity here? For this, we just define slightly more. So our function phi 1, so we define a sequence of functions phi n, all compactly supported and continuous. And phi 1 is defined by starting with the first subdivision operator we chosen, and phi 2 is nearly the same, but we skip the first subdivision operator and start directly subdividing from the second. And then if we define this sequence, then we get this self-similarity equation here that the n's limit function phi is a sum of shifts and dilates of the n plus 1s. I think there's a, yeah, like that. So now we have the definition, and now my target is to show how can we prove that a given subdivision, multiple subdivision scheme is convergent. For this, we need to make a slight detour to attractors and ties. And again, first in the single case. So we have a mask and a dilation matrix. So the mask was the data generation rule, and the dilation matrix, how our mesh is refined. Then, and for the dilation matrix, we now define a digit set D, which are representatives of this group ZS modulo MZS. And then one can show that for any point in the in RS, any vector, we can write it as an integer part plus a fractional part, where the fractional part comes from this set here. So in this set are all points which we can write in this way. And so this looks quite funky, but it's actually something very familiar. Because if we take m equals 10, d the digits from 0 to 9, then x is the set 0 to 1. So this is actually then the decimal number system. So we have here. So this kind of writing here is just writing a number in a number system with a matrix space. And so for this slide, I will adopt this notation here. So 0 dot first digit, second digit. And in the if you're in multiple dimensions, these digits are vectors. So another example in 2D is this with the dilation matrix 1, 1, 1, minus 1, and these digits that we get on parallelogram. If we change the minus from slightly, we get the twin dragon we saw at the beginning. So one can make very beautiful pictures with this. And so what have we gained now by writing a number like this way? So we have a look at the self-similarity equation. So phi is the sum of shifts and dilates, a finite sum of shifts and dilates of itself. And first we plug in omega plus x for y and make a trig by adding and subtracting d1 and shifting the minus d the plus d1 to the mask. So now this was nothing but algebraically manipulation. And now we let run omega over all integers. So we have an equation of vectors now. This is an infinite vector. And then if you have this vector, if one looks at this, one sees this is a matrix vector multiplication of an bi-infinite vector matrix TD1 times an infinite vector here. And now the nice thing is the stuff which remains here is mx minus d1, and this is exactly, we have a look here, the number 0, comma d2, d3, d, and so on. So we can pull out another bi-infinite matrix TD2 and so on. So what we have gained here is that we can compute all function values of our function phi using an infinite matrix product of bi-infinite matrices. So that's very great. What's for the multiple case now? We add just a lot of indices. So we have a finite set of subdivision operators, masks, and dilation matrices. For each matrix, we need to choose some digit set. Additionally, we choose a subdivision scheme, so how we want to apply our subdivision operators. And then the only larger difference is the definition of our attractor X, so the set of all fractional numbers, which instead of matrix powers now consists, here of matrix products. And then by doing the same calculation as before, we obtain that phi n is can be written as a as an infinite product of bi-infinite matrices, and those matrices now depend on the digit and on the sequence with the we've chosen. So clearly, working with bi-infinite matrices is not that great, and with infinite products also, but bi-infinite matrices are, I think, even worse. But the nice thing is these matrices are kind of diagonal. So there's it can be quite broad, but it's actually a band of values on the diagonal, and the rest is 0. So one can show that for any set of subdivision operators, Aj and Mj, there exists a finite dimensional subspace, so sequence supported on some finite subspace of CS, on which those matrices TDJ, these bi-infinite matrices, are invariant. And this set omega can actually be constructed explicitly, and we also have some kind of minimality results for this set of omega. Clearly, we want some small set omega because this makes our matrices smaller. And then if we have our set omega, we can even use this set to bound the support of our limit functions by expressing them as integer shifts of this set of all fractional points we've seen before. And then the important part of the theorem is it turns out that these restricted matrices to this set subset omega have another invariant subspace which turns out to be just the vector or orthogonal to the vector of 1. And if we restrict these matrices again, we can show that curly S is convergent. So any possible sequence of subdivision operators, any possible subdivision scheme is convergent if and only if the joint spectral radius of those restricted matrices is less than 1. And the proof is easy because the joint spectral radius equals this restricted spectral radius, and that's it. So we go on. Okay, what is the restricted spectral radius? The restricted spectral radius just measures the differences of consecutive numbers in the sequence we are generating. So nabla R is the directional difference operator. So the restricted spectral radius just looks at all possible in all possible directions over all possible subdivision schemes and all possible starting sequences. And if the consecutive differences go to 0 sufficiently fast, then we can expect that the subdivision scheme is convergent. So, and to show that these two numbers are the same, actually boils down to showing that this vector orthogonal to the vector of 1s is the same as this vector space here. In this vector space is the span of all vectors of 1 minus 1. So the directional difference in direction R of the delta sequence, and we shift this vector of 1 minus 1 around in our space L omega and take the span of it, and these two vector spaces coincide given omega is fat enough. So there's some small conditions on omega, but they are quite technical and boring, so nothing deep. And if we have this, one can show all norms which arise in this equation are equivalent, and so on. We are done. So now we know how to check that the subdivision scheme is convergent. We just have to compute this joint spectral radius, and this leads now to the second part of the talk. How can we compute the joint spectral radius? So again, the definition. Interestingly, the joint spectral radius was invented in 1960 in a small paper in a small journal, and it was not really recognized until much later, I think by Dubuchy, but yeah, so and now it turned out to have a broad field of application, the joint spectral radius. So again, the definition, we take, given a set of matrices, we take all possible matrix products of length n, its norms, average it by the length, and take the limit. So except if you're really optimistic, it's quite understandable that it is mostly an NP-hard problem, which it is because the number of matrix products of length n increases exponentially with n. But it's actually even harder. For example, the question whether the joint spectral radius of a given set is less or equal than 1 is undecidable. So this means there is no algorithm which can determine in finite time for all possible sets whether this is true or not. So and so it's no surprise that there are a lot of algorithms which try to compute the joint spectral radius. There are a lot of algorithms which do it approximately, but only two which can do it exact. One of them is the invariant polytope algorithm. I will abbreviate it with IPA in the following, and another one is by Claudia Möller and Ulrich Reif. Uli will have a talk tomorrow. But in the following, I will only talk about the IPA actually. So, and the IPA mostly is based on, no, not mostly, but it uses one theorem by Dobeschi and Lagarias from 1992. And this theorem gives lower and upper bounds on the joint spectral radius. And it says, given any integer and any submultiplicative norm, then the spectral radius of any matrix product is a lower bound, and the maximum over all matrix products of length n in norm is an upper bound. So if we're optimistic and we want to exploit this theorem in a fancy way, we can hope that we will find a matrix product of finite length which already attains the joint spectral radius, and we will call such a matrix product spectral maximizing product, SMP. And on the other hand, this theorem holds for any integer, in particular for k equals 1, and also for any norm. So we could hope that we find a norm such that the joint spectral radius is attained for matrix products of length 1. And if we have this, we can construct such a norm. We have a strict lower and upper bound, so we computed the joint spectral radius exactly. And now the IPA exactly tries to do this. So I will give a, I will show how it works now, the IPA, on a concrete example. So we have two matrices. So the example is in 2D, so I can draw beautiful pictures. And in the first step, I make a guess that the spectral radius of B equals the joint spectral radius. And I'm really good at guessing. So B is now at the SMP candidate. And then we normalize the matrices A and B and A by the spectral radius of B. And now in the second step, we compute the leading eigenvector of B. So here's a typo. This is actually a B. So the leading eigenvector is the eigenvector corresponding to the largest eigenvalue in modulus. And then we look at the invariant, at the polytope defined by this vector. So this is a degenerate polytope now, but we tried to construct an invariant polytope starting from this. So we look on all pictures of this point V0. B V0 is the same, so only so it's contained in the image, but A V0 is outside. So we add this to our invariant polytope and have a look whether this polytope is invariant. Because the boundary are straight lines, we only have to consider always the edges. So in this case, we have to consider two children. The green one is, I think, this was BB, no, A. Yeah, this is A V0, and the red one is BA V0. BA V0 is outside, so we add it to our invariant polytope, our not yet invariant polytope, and look at all children of this vertex. One is inside, one is outside again, so we do it. One is outside again, we do it again. And now all children are inside. And what have we gained? What have we got now? This black thing now, this black polytope is invariant under matrices A tilde and B tilde. So now we construct the vector norm with this unit ball, and then look on the induced matrix norm. And by construction, then this matrix norm of A tilde and B tilde is less or equal than 1. And that this means that the joint spectral radius of those two matrices is less or equal than 1. And equivalently, the joint spectral radius of AB is less or equal than rho, which is the spectral radius of B. So we have a lower bound rho and an upper bound rho. So we computed the joint spectral radius exactly. So that's the idea of the invariant polytope algorithm. So here's another picture in 3D. The nice thing about this algorithm is you can make really beautiful pictures if you don't know what to prove currently. So in this example, our SMP has length 4. It's ABBB. Here is a picture of the invariant polytope, and this is a tree which encodes all the vertices of it. So the black dot is the leading eigenvalue of the leading eigenvector of pi, and then a green vertex is multiplication with B. So here is B V0 inside, A V0 inside, B A V0 inside, A B A inside, and A B A no A B A V0, so and so on. Yeah. And so yeah, we can say when does this algorithm terminate, and there are 3 conditions, and if they hold, then it terminates, and if it terminates, the condition holds. The conditions are: first, there exists finitely many products attaining the joint spectral radius, so there's the spectral maximizing products. So forbidden is sets where no spectral maximizing product exists, and also the case when there exists infinitely many products. Then second condition is each spectral maximizing product must have only one simple leading eigenvector. So there must not be 2 eigenvalues with the same value in modulus. Say 2 leading eigenvalues with the same value in modulus. And the third one is that the set curly A has a spectral gap at the joint spectral radius. So any matrix product has the spectral radius of any matrix product is either the joint spectral radius or is bounded strictly away from the joint spectral radius. So it's not allowed that the matrix product slowly approach the joint spectral radius. And if these 3 conditions are satisfied, then we know it terminates. Unfortunately, we have no characterization of the third point, so about the spectral gap, except that if this algorithm terminates, then there is a spectral gap. And the same for the tree algorithm from before. If the tree algorithm terminates, then there's a spectral gap. So, so that was the original, more like the original IPA, and now I will show some modifications or advances we could do so far. And first thing is this guessing of the SMP. So one problem about the spectral maximizing product is, which we need to guess, is not only if we guess it wrong, then we have a bad lower bound, but also if we guess it wrong, then the construction of this polytope we're doing cannot terminate. So it's quite important to make a quite well guess. And for that, we modified the algorithm by Gripenberg, which is actually used to compute lower and upper bounds. And I modified it in a way that it computes good lower bounds. It's actually just a heuristic, but it works quite well, and it keeps the number of matrix products bounded. So we can have a look at really long matrix products. And just for advertisement for my algorithm, here's a table about some test results. So given random matrices of dimension 8 and sets of 8 matrices of such, then the modified Gripenberg algorithm in average needs 5 seconds to find the correct SMP. All other algorithms are much slower or do not work. Clearly, the giant spectral radius computation is NP hard, so this algorithm sometimes must fail. And in that case, not all hope is lost, because the invariant polytope algorithm has means to construct better SMP candidates while it's running, but this is kind of slow. So that's why I wrote here the invariant polytope algorithm is slow, but has an approximate asymptotic success rate of 100%. But it's better to guess it correctly at the beginning. And then for the second step, so the construction of the invariant polytope, what can we do here? One thing is that the input matrices we are using have a quite obvious, quite large influence on the behavior of the algorithm. But actually more than one can imagine, because there are two special cases actually. If there are probably more special cases, but currently we have two special cases. So if all input matrices are positive or non-negative, then we can construct the polytope, which is much larger. And so the algorithm is much faster because more points are mapped into the inside. So the polytope we are constructing is more likely to be invariant. On the other hand, if the leading eigenvalue of our guessed SMP candidate is complex, then we have bad luck and need to consider polytopes, which are the convex hull of ellipses in space, or so ellipses in the S-dimensional space, but still ellipses, so the 2D thing. And this makes the problem much harder. Then we can also add extra vertices to our polytope from the very beginning. So in the example we've seen, where we constructed the invariant polytope, we started with the line segment. And the line segment is unlikely to be an invariant polytope. So by starting with something slightly larger at the beginning, the algorithm usually is much faster. And then, interestingly, the algorithm is very sensitive on which eigenvectors you choose. Since in some examples it's sensitive. In some examples it does not matter at all, but in some examples it can happen that with one set of eigenvectors, the algorithm terminates after a few seconds. So we know all the 3 conditions are satisfied, but if we choose another eigenvector, then the algorithm suddenly takes days. So we currently have no mathematical description which eigenvectors to use, but we have a kind of canonical heuristic in the sense of use as little starting eigenvectors as possible. And then, of course, the algorithm can be parallelized. We can guess solutions of subproblems we need to solve, and also do some informed search in the tree. So in the example, we did a first search, first all products of length 1, then all products of length 2, then all products of length 3. By changing this, the algorithm is also much faster. And then currently we are trying to do the following. If we have a vertex, also an image of a vertex, and this vertex happens to be exactly on the boundary, then numerically we cannot determine whether it's inside or outside. And so numerically we have to say it's outside, of course, because we want rigorous results. By using a mix of symbolic and numeric computations, we can solve this problem quite nicely. Of course, this usually only works in low dimensions when we can write everything explicitly. Otherwise, we have to use roots of polynomials and all this stuff. This is not nice. And then another thing we're thinking about is that for the input set, we can add some matrices to it. And we know if we add those, we do not change the joint spectral radius. And so our hope is to find some matrices to add such that the algorithm is faster. We already have some examples where it works, but we don't know what are the connections between those sets. And then another thing is currently the IPA searches for a norm under which also a polytope which is invariant under all matrices. We can relax this by searching a polytope which is invariant under matrix products of length k. And this k can actually be quite large. So currently we're working something with 500. And this works nice in some examples, in some not. So this is, like the title says, all experimental. And at the end of my talk, I will just show some applications. So everything you've seen is implemented in MATLAB in the T toolboxes, which can be downloaded here. And so there are functions to work with subdivision schemes. So functions to print the limit functions, or the vector x, the point of the set of all fractional points with respect to some matrix space, or the support of the limit functions, and also the invariant polytope algorithm is implemented with the name TGSR. The T stands for invariant polytope algorithm. It has nothing to do with my name, Thomas. And yeah, transition matrices constructs the matrices T, and construct V constructs this subspace, orthogonal to the one, and so on. And we use the IPA, for example, to compute the regularity of Debussy wavelets. So similar to check whether the limit function is continuous for certain subdivision schemes, we can also compute the exact regularity. And with the first version of the IPA, Guglielmo and Botasov were able to compute it up to the 20s. And then currently we can compute it up to the 40 seconds. I don't think this has any application, but it's nice at least. And for the rest, we have upper bounds currently. And then another thing we could prove is the following. There's at the beginning of the joint spectral radius, not at the beginning, but for a certain time, there was this conjecture that any set of matrices possesses a matrix product which attains the joint spectral radius. This was called Finiteness conjecture, and it was proven to be wrong. So there are even counterexamples of 2 times 2 matrices. But surprisingly, all matrices from applications seem to have this property. So for all matrices we have seen so far, there always exists a finite product which attains the joint spectral radius. And there's a theorem by Schwinger, which states that the finiteness conjecture holds for all non-negative rational matrices if it holds for all pairs of matrices with entry 0, 1, and a similar theorem for all rational matrices. For those, the finiteness conjecture holds if it holds for all pairs of matrices with entries -1, 0, and 1. And with the IPA, we could automatically prove this theorem for 0, 1 matrices with dimensions 2 and 3. And also for matrices of dimension 2 with entries of -1, 0, and 1. And yeah, that's for my talks. Thank you for listening, and I hope you have a lot of questions.
Okay, thanks very much, Dr. Mejstrik. So please, questions.
Oh, I was very fast. Wait, I think I spoke too fast.
Maybe I begin with questions.
I also have a question. I
Constanza, yes.
raised my hand. In the back, probably you don't see it. No, I have a general question, Thomas. When we complicate the subdivision, for example, going from stationary to non-stationary, I'll talk about it tomorrow. We gain something, for example, in terms of type of function that you can generate. We know, for example, that we can generate exponential polynomial going from stationary to non-stationary. And in this situation with multiple subdivision, you have a full generality because you can change your rarity at each step. Do you know if you can gain something like properties of the limit function or reproduction properties, these things?
Not yet. The problem is with this theory, we need only have a finite set of subdivision matrices. So in non-stationary, you can have an infinite set of subdivision operators. They just need to converge somehow.
Yeah.
And now currently, we need to have, actually it must not be, it doesn't need to be finite, it must be compact somehow. So the mask of the subdivision schemes must be bounded. And so apart from generating multi-resolution analysis for directional features, I don't know what we could.
You could, for example, change the first step and then going on with one fixed subdivision scheme, like more or less asymptotical equivalence does.
Again?
I mean, for example, if you have a scheme, a non-stationary, which is asymptotical equivalent to another one,
yeah,
you essentially work differently on the first steps, and then you work like with the asymptote. So in some sense, even if you can have only a finite number of different operators, you could gain something.
Yeah, I'm actually trying around a lot, but I haven't found yet something really special, unfortunately.
Thank you.
I have a question about the following problem. Of course, talking about multiple subdivisions, which you presented, we must be ready to the increase of the number of matrices. Yes, so we have like two positions for the matrix M for the dilation matrix. Yes, M1, M2. So this means that the number of matrices you have to analyze for the Jones spectral radius doubles. Yes.
So it's linear in the number of schemes and the determinants of the matrices.
And what about the complexity of your algorithm? So, I mean, can it be kind of parallelized or what? So if you have not like two matrices by 4 or 6.
There's not a big difference if you only have 2 or more matrices, actually. There are examples where examples with 6 matrices which are fast and examples with 2 matrices which are slow, and vice versa. So I don't think that the number of matrices is some significant parameter of the runtime of the algorithm.
Okay, more questions?
Is there some good standards team which matrices is better to use? For example, if I want to construct a multiple subdivisions team with 2 matrices, is it better to change their each iterations, or for example, to use the first matrix for some number of iterations and then switch to another one? Are there any empirical recipes, what is better to use?
Better in which way?
For example, some subdivision schemes, properties, maybe a rate of convergence.
Okay. Currently, we can only, so for stationary subdivision schemes, you can compute the smoothness. So we can compute some rate of convergence. For multiple subdivision schemes, we only can compute the rate of convergence for a fixed subdivision scheme, not over the whole set. And in particular, we can compute the worst case Hölder regularity. Apart from that, I have no heuristics how to generate a very good subdivision scheme, unfortunately.
Okay, thanks. I also wanted to ask if you could tell some statistics about how invariant polytope usually looks like.
So usually it has I think that is kind of
like what is a typical?
Yeah, usually it looks like this actually. So at least in 3 dimensions, but if I have a look on projections of polytopes from high dimensions into R3, they look also very similar. So they are quite long and tilted and have a lot of points. So kind of a lot of points in one area usually. So for example, in this plane, there are a lot of points. And in high dimensions, they can accumulate quite heavily in one area. So the points are very uneven distributed of the polytope.
And the number of vertices is usually not very small, yes?
The number of vertices is actually surprisingly small. So given that the number of vertices increases exponentially with the, if you have a look on the unit cube in Rs, then the number of vertices of it increases exponentially with the dimension. So already in dimension 20, it's too much. But usually in dimension 20, so for examples where I have 2 matrices with the same spectral radius in dimension 20, the limit that the invariant polytope has around 4,000 vertices, which is surprisingly small for this dimension.
Yes, thank you.
But as far as I can see, so first of all, vertices are not distributed uniformly. Let's say on a sphere, yeah. If we project them into the sphere, they are not uniform. And is it correct that the invariant polytope doesn't look like an ellipsoid? Let's say, I don't know how to express it properly.
I don't know if it looks like, but I don't believe it's really an ellipsoid actually.
No, I mean, maybe I'm wondering whether kind of Dvoretsky theorem could be applied here, that for high probability, the vertices are distributed like for an ellipse or not. Because from this picture it does look like that, yeah, but here, of course, not so many vertices here. Mm-hmm.
Yeah, there are pictures where the invariant polytope totally looks like an ellipse actually, but so I have one example where in dimension 2, where the SMP has length of 119 and the polytope has 238, no, even more, roughly 300 points on the boundary, and it looks like 2 ellipses, but I don't think it's really an ellipse.
Mm-hmm. Mm-hmm. Thank you. More questions? So if not, I would suggest to thank all speakers for today's session. Tomorrow we have the second session in the same time, so in Moscow at 5 and Europe at 3. We have 3 lectures tomorrow of Professors Ulrich Haif, Costanza Conti, and Carlo Mani. And so everybody is welcomed. Thanks for the attention. Great thanks for the lecturers who could devote some time with this very busy period of teaching in this semester. And so thank you. See you tomorrow in the same Zoom conference.
Okay, thank you. See you tomorrow.
See you.